Hello, and welcome to this course on designing a data model in Power BI. Just as important as building a data model is knowing how to deliberately design the data model for best performance, high-quality insights, and user-friendliness. My only prerequisite for this module is a familiarity with preparing data using Power BI. When you have completed this course, please do take a moment to rate it, as this valuable feedback helps us deliver high-quality training to you. Let's start by defining a data model. A Power BI data model describes a collection of data brought together and made relatable so that analysis can be performed. Data models often include data from various different sources. Because that data often comes from different sources, most data models require logical relationships to be established between the data sources so that data from those different sources can be analyzed together. Most of the time, we will need to define or program the relationships between the data ourselves. And the way we define these relationships is extremely important as it has various downstream impacts. Furthermore, not all data will automatically play nice with the other data in the model. So much of data modeling competency involves being aware of common problems, recognizing problem indicators within our datasets, and having the tools to resolve those items before they manifest as issues downstream for the user, which is why this module is so important. Now, all data is different, so one size does not fit all when it comes to data models. But all data models do seek to have a design that enables fast navigation through the data, the design of simple measures and calculations, aggregation accuracy, of course, ease of report creation, and simple report maintenance. In this course, we will begin by defining the elements of an ideal data model. We will approach data models' various components, starting with tables, relationships, and explore the impact different relationships will have on our reports. We will learn how and when to adjust table and field settings to ease information flow between the tables, and create some quick measures to help us get started building reports. We will talk about the natural occurrence of hierarchies in our data, how they can be used, and how to flatten them when needed. Date tables are also covered as a solution to common date analysis issues. The important concept of data granularity is discussed so that we can make the best performance decisions for our data models. And we will round all this out by covering other performance considerations and how to set ourselves up for success. Let's begin. There are lots of ways to define a good data model. And in this course, we will be talking about model schemes to achieve best performance and strategic relationships to obtain best data flow and other vital functional items. But I'd like to start by talking about what it means to have a good data model from our user's perspective. Now, we may be designing a data model for ourselves, or designing it for colleagues, or for clients. But whoever the end user is, if they can't use it, all the analysis power in the world isn't worth much. So let's start here by keeping the end user in mind when designing a data model. First off, data models that are complex or convoluted take more time to navigate, require more complex data analysis expressions, and can just be frustrating for the end user. Simple models, on the other hand, offer a shorter startup time and more energy can be spent on discovering insights. So it's good to simplify our data models as much as possible. In this video, we're going to look at some of the ways data models get messy, and they just about always do get messy, and ways to simplify them and tidy them up. Data models that have fewer tables are just easier to navigate. The model view in Power BI gives us an eagle-eye view of our data model. Each box in the model view represents a table in the model, and each line in the boxes represents a column in that table. If too many tables are added to the model, it can just be visually overwhelming for the user. And also, too many tables can sometimes cause functional issues or even lead to report inaccuracies. So this is why it is super helpful to know when you can and should consolidate your data into fewer tables, and how to do that. In this model, I have these 3 tables, which are queried from 3 different sources that contain the same type of data. Notice that even though they come from different sources, their structure is really similar, and they all also have the same level of detail. This is a really common real-world scenario, and it's a great example of data that can and should be combined into a single table. In this case, we would append the data using the append tool in the query editor. The append tool will keep the columns just as they are and just tack each table onto the bottom of the previous table, so they become one long table. We'll start by opening the query editor by clicking on Transform Data. Inside this command group, I'll find my append tool. I do have 3 or more tables, and we'll see this current table is already included on the right side here, so let's add those other 2 tables and click OK. And because we're being really mindful right now of our end users and our model's readability, I'm just going to rename this query right now to better describe this new combined data table. All right, I have now combined that data into one table, but looking here, I can see those precedent tables where I got that data. They're still hanging out there in my model. You can actually remove them from that model view from right here in the query editor. You can right-click on the query and turn off Enable Load. This safely removes from the model view without ruining any of the dependent queries. This one adjustment we just did some important things. It removed some visual clutter from our model, but I have also exponentially multiplied my analysis options by consolidating all of that data into one table. Now I can analyze those regions together. I can also compare them to each other. I can drill down into segments of those regions for a more granular analysis, and I can look at those at the same time on the same visual. This is a win-win. Every column that isn't needed should be removed from your data model because every column adds a data point for every row in that data set. So in the case of fact tables or long tables, for instance, each column can actually add millions of additional data points. And this affects the performance of your data model in longer scan times, longer load and refresh times, and it can throttle your computer's memory. In addition to that, it's just not very user-friendly to have 100 columns to scan through to find the relevant field. So every column we don't need should be removed to improve performance and readability. But there are cases when even though the report builders won't be using it on their reports, we can't totally remove it because it's essential for some important calculation or security settings. These can actually be hidden from report view to reduce that visual clutter. You can do this from the model view by right-clicking the field and choosing Hide in Report View. You can also do this from Report View by right-clicking and choosing Hide. You can even hide entire tables if they aren't necessary in Report View. The following tools are going to allow us to make our model view more readable as well. First of all, we have a lot of flexibility to adjust the model layout. We can just click and drag to move tables in a more logical arrangement. If you find you need to scroll to see all the tables, remember that you can scale to fit using the button in the bottom right along with that zoom slider as needed. But even tidied up models can look excessive if the reader is only there to consume a small portion of the data model. For this reason, Power BI introduced a feature that allows us to focus on a subsection of the model. You can start by adding a new View tab at the bottom of your modeling view, and then we'll open up our field pane and drag in just the tables we care to see in this view. We can right-click on a table and choose to bring in its related tables. When I've got it the way that I want it, I'm just going to make sure to name it so that the users that need it will be able to read it. After carefully combing our model and removing dispensable data and consolidating information, our users will be able to hit the ground running and have a much better experience within our data models. Now that we have a better understanding of what makes a good data model from the user's standpoint, let's delve into designing data models for technical performance. Data models are made up of tables and relationships. The way the tables and relationships are laid out is referred to as the schema. We have all seen one very common type of schema, the flat schema. The flat schema is tables. These are two-dimensional with columns and rows, and they work great if your data is under a few 100,000 data points and your goal is to perform some basic analysis on a column of data. The limitation of this model is that adding just one column results in adding one data point for every single row that already exists. So when we start handling big data in the hundreds of thousands, tens of millions, even billions of records, we need to move to a dimensional schema, which is when we graduate to the star schema. The star schema can ignore the irrelevant data in the model while running a calculation. The star schema is so named because it usually has one central events table which has relationships to a number of detail tables. When we use star schemas, we segregate the data into two purposes: fact data and dimension data. Fact data is a list of events that drive a business process. The data is usually calculable, and the fact tables often have records in the high thousands, millions, and billions. Think of sales transactions. Each transaction is an individual numerical data point, and we calculate those data points to measure business performance. Dimension data, on the other hand, is all the details that describe the fact data. Dimension tables contain categories and subcategories, locations and business channels, client areas, and employees involved in the fact events. Each cluster of dimension data gets its own table, so we tend to have multiple dimension tables. We use this dimension data to describe the fact data. And because the fact data measures in the millions, we need to distill all that information down to a small, understandable measure. This process is called aggregation. Aggregation is the process of taking a bunch of numerical data points and measuring them in such a way that produces a single numerical representation of all that data. You already know the basic aggregations like sum, average, count, min, and max, etc. While data tables make up the bulk of a data model, relationships make the frame. Relationships are the bones and tendons and ligaments that create structure. Without them, we would have a flat, gelatinous blob of data. Power BI has a relationship auto-detect feature that's pretty good, but it doesn't always get it right. So it's important that you know what a proper relationship works like and how to repair problematic relationships. Tables alone can't talk to each other. Let's take these two tables. Our fact table lists all the transactions, but by looking at these transactions, we can't really tell what happened. We can see some amounts, but amounts of what? I can't tell because the only identifier are these IDs, and they don't really mean anything to me, the human. But I do think that I've seen these IDs somewhere before, on our products table maybe? Oh, there it is. The Fabricam laptop white, which matches product key 345. So using my human logic, I can compare these two matching IDs and confidently determine that this was a sale of Fabricam laptop white. That's what relationships do. They connect items from table A to their matching items in table B. If we have no relationships between these two tables, but we attempt to create a visual using data from both tables, we are going to get this weird result where the numbers all look maxed out. What's happening here? Well, we're seeing all the product labels listed, and we're seeing all the sales listed. But the sales numbers aren't being categorized by product. The model is simply listing all in each table. If I go into Model View and create this relationship, I am teaching the model that when you see product ID 345 on the fact table, connect those IDs to the matching product IDs on the products table. Now our model can identify the sales that involved Fabricam laptop white and summarize that information for me. And not only can it do this for Fabricam laptop white, it can do it for all the other products as well and show me the results in a nice, tidy visual. This is why relationships are critical in data modeling. It is very rare for a table to be completely disconnected from the rest of the table. But not all relationships are the same. Let's learn about the special behaviors of different types of relationships. While your modeling career will undoubtedly involve plenty of properly functioning relationships, you will also inevitably encounter problematic ones, and you'll need to know how to resolve them. Let's take a look at the relationships in this model by selecting Manage Relationships from the Home ribbon in Model View. Each line represents a relationship in our model. Let's open one to take a look. So this is an active relationship between the fact sales table and the channel table. And it uses the columns called channel key in each table. Below are two drop-down menus, and they represent very important topics. Relationship cardinality describes the parent-child-like relationship between the values in each column. And there are 4 different types: many-to-one, one-to-one, one-to-many, and many-to-many. Cardinality describes how items in the first column behave as a set, and also how items in the first column match with items in the second column. You very well may encounter every one of these cardinality types, so let's get to know them. The many-to-one and one-to-many cardinalities describe twin scenarios. If we have 2 tables being related, in one of these tables, we are going to see the channel each listed only once. In the other table, we are going to see the channel listed many times. This describes a one-to-many relationship. The only difference between many-to-one and one-to-many cardinality types is which table is selected first in this Power BI dialog box. If I swap the tables around, notice it just flips those terms. Makes perfect sense. Many-to-one and one-to-many cardinalities are the most common type of cardinality, but the other ones are there for a reason, and we will run into all of them eventually. One-to-one is a cardinality for which each record in Table A is associated with one and only one matching record in Table B. For example, this company has one store manager for every store. When the store manager table is related to the stores table, since each store has only one manager and each manager only manages one store, this will create a one-to-one relationship. I can visually identify this by looking at the endpoints of this relationship, where I can see a number 1 on each end. This relationship is simple and pretty user-friendly. The many-to-many relationship type describes a scenario in which Table A has parent values for which there are multiple children in Table B. And those same children can act as parents in Table B, having multiple children in Table A. A common example of this is orders and products. One order might list many different kinds of products, and each product has probably been purchased in many different orders. Many-to-many relationships were not allowed in Power BI until 2018. And the workaround for these types of relationships was to create a bridge table that contained a list of unique values from both tables, and then relate this unique table to both of the many tables. Then, in 2018, Power BI introduced the many-to-many relationship type, which made it a bit easier to handle these relationships in Power BI, but as we're about to see, there are still lots of limitations. Often the reason for a many-to-many relationship is that the data has not been properly separated into a star schema. You'll find dimension data in the fact table alongside the fact data, which flattens out the model. And because all descriptive data is now being populated a million times, all that descriptive data becomes many data. The solution to these scenarios is usually to star schema the data. When possible, pull all your dimension data out into dimension tables. Let's see a real-world example of this and see how to resolve it. Here, we have some basic information about one of our competitors' sales figures by channel and also by product. The first comparison we want to run is a side-by-side comparison of channel sales. So let's start by relating channel names to channel names. We are pretty much relating to fact tables here, so those channel names are going to show up many times in each table, resulting in a many-to-many relationship. Visually, I can tell that it's a many-to-many relationship by looking at the line between these two tables. Notice that the asterisk appears on both sides, indicating a many-to-many cardinality. Okay, let's try creating our side-by-side comparison of the channel sales. We'll start with our sales from our own fact table, and then add their sales, and then segment it by channel name. Cool, I can see our sales and our competitor sales side by side. While this exact analysis works, I have very little flexibility with my analysis options here. Watch what happens if I try to parse it out by product category. And there we can see that dead giveaway that we have an issue with a missing relationship. This is happening because we specifically related these two tables by channel name, so that's the only related data. So we would need to go back in and add another relationship. Let's see. Switching to model view, dragging and dropping product name on product name, and click OK. And now it appears as a dotted line. This is because it's an inactive relationship. And it's an inactive relationship because there can only be one active relationship between two tables at a given time. This is for very good reason. It prevents circular filtering issues. So we would need to deactivate the channel relationship to enable this new one. This obviously is not very user-friendly. So the real, lasting, and smart solution is for these two tables to both be filtered by dimension tables. And in this example, our competitor's data is super flat. So that is half the problem right there. Convert this flat table to a star schema. Pull out the dimension data, and if any of its dimension data is the same as the dimension data from our model, relate them both to that dimension table using one-to-many relationships. This solution would allow our users to filter our data side by side with our competitors' data using any relevant data, and they wouldn't need to deactivate relationships or program any complex stacks to do that. One of the reasons star schemas are so effective with large datasets is due to filter propagation behavior. Let's start by noting the one-to-many relationship between the product categories and subcategories. In these one-to-many relationships, filters applied to the one table are transferred to the many table. And if that many table is also a one table in another relationship, then that same filter gets propagated down the relationships from one to many until it reaches the fact table. So if we filtered the product category to only audio, the subcategories get filtered for only audio as well, as do the product names on down. And each different one table can be filtered, of course, which results in the final table, the fact table, inheriting the filters from all of its parent tables, grandparent tables, and great-grandparent tables, and so on. The direction in which filters are inherited between two tables is referred to as the cross-filter direction. While we've seen only one type so far, there are actually two types of cross-filter directions possible in Power BI. The single cross-filter direction is the one we've already seen. This allows filters on the one table to flow to the many table. This is the default cross-filter direction for one-to-many relationships and also the most common. In single types, filtering the many table does not have any impact on the one table, but there are cases when you might need filters to be able to flow upstream, if you will. This bidirectional cross-filtering is referred to as both in Power BI. This cross-filter direction is generally discouraged as it can potentially cause problems, but sometimes it's the best way to get the job done. So let's learn when we can use it and when we should absolutely avoid it. Many-to-one and one-to-many relationships are by default assigned the single cross-filter direction, but you can change them to both when needed. Let's see an example. The most common reason to adjust cross-filter direction to both is to sync slicers. For example, on this visual, notice that when I select customers, my other slicers are not being filtered to show the available categories and colors for that customer. For instance, our customer A Datum Corp does not purchase any home appliances from us, but you wouldn't know that from the slicer. The slicer implies that home appliances are a valid category for this customer. But when I select home appliances, the whole visual goes blank. That's because they don't purchase any home appliances. The reason why the slicer isn't being filtered is that filtering the customer table for A Datum Corp only flows down to the fact table where it stops. This filter won't swim up any of the other streams to filter those upstream tables, unless we adjust the cross-filter direction. If I change the relationship between these two tables from the single cross-filter direction to the both cross-filter direction, notice that the icon changes from a single arrow to a double arrow. And if I return to my report and select the slicer option, now the other slicers are automatically filtering themselves to display only relevant options. This was simple and easy and got the job done. But behind the scenes, some important things happened, and this one seemingly small adjustment could cause problems for us if we aren't careful. Sometimes the both or bidirectional cross-filter direction introduces ambiguity into the data model, which means that there are multiple paths that Power BI could use to propagate filters between tables. Luckily, we do not have any of that in this model, but let's create a fictional scenario to better understand this real-world problem. Let's say we had a brands table, and that brands table could be used to propagate filters to the products table and also to the orders table. In this scenario, this bidirectional cross-filter we created earlier would introduce ambiguity into the model because there would be two different paths that brand filters could be propagated to the products table, either directly from the brands table to products table, or from brands to orders customers to fact sales to products. Power BI's algorithm is pretty smart in guessing which route is best, but it's not smarter than humans, so it's up to us to help Power BI avoid these ambiguous scenarios. Earlier, we saw that it's possible for two tables to have multiple relationships between them, and we noticed that only one relationship can be active at any time. Usually this happens between a dimension table and the fact table. One of the most common scenarios is when you have two different date fields, for instance, sales date and ship date. They both need to be used in different scenarios. Non-active relationships can be activated by using some custom DAX. And for each custom measure, the date table can play different roles with the fact table, which is why these are called role-playing tables. So now we know that relationships come in a lot of flavors, and they are absolutely critical elements of data models. But not all relational problems are caused directly by relationships. Having granularity disparities is another major culprit we want to be aware of. Let's dig into the concept of granularity. The term granularity refers to the level of detail within the data of your model. High granularity means that you can see lots of minute details, while low granularity means you see fewer details and focus more on the bigger picture. There are pros and cons associated with each, and so each model will have a unique definition of ideal granularity. Each table will have its own level of granularity too, defined by its smallest measurable increment. Date tables that go down to the day will support analysis on changes over time down to the day. This might be perfect for a marketing company determining the efficacy of certain marketing campaigns throughout each month and year. But other industries require much more frequent measurements, such as power companies, who often measure down to the nanosecond. That high granularity is needed for power companies, but if the marketing company measured in nanoseconds, their data model would be preposterously huge and unnecessarily slow. When determining the appropriate level of granularity for your model, you can ask, what level of detail is expected by report consumers or by report authors? And also, will your model's insights be compared or used next to results from other analysis systems? If so, the granularity should probably be as similar as possible. Once you've decided the right level of granularity for your model, make sure all dimension tables and the fact table can be measured as increments of that granularity. There is a whole language of functions in Power BI, but before we are ready to deep dive into the world of DAX, there's a neat feature that will help us make our measures called quick measures. Let's say we want to calculate the profit of each sale by subtracting the cost from the gross sale amount. We can create a quick measure by selecting the table where we want this measure to live and find Quick Measure on the ribbon. Or we can right-click any field and choose New Quick Measure. In the Quick Measure window, let's scroll to the mathematical group and select Subtraction. In the Fields pane, let's expand the fact sales table so we can find our gross sale amount and drag it into the base value box. Drag the sale cost field into the value to subtract box. And just notice that each of these fields are going to be aggregated by sum, and that sum is going to happen before the subtraction happens. We'll select OK, and there it is. Notice the new measure has a calculator icon next to it. This is how you can visually identify them. That was easy. Quick measures are that easy. Most businesses need to create calculations based on time to track changes over days, months, and years. So it's important that our model has a dimension table dedicated to parsing out and grouping time increments that are relevant for our business. There are different ways to get a date table. Often, data warehouse developers will have already created a date table for your model. In these cases, you should use the warehouse model because it likely has appropriate time intervals and company dates, alternative year start and end dates. But not everyone has this at their disposal, so let's learn how to build one ourselves. Among the library of helpful data analysis expressions in Power BI are a group of time-related functions to help you start off a date table. We have Calendar Auto and Calendar. These DAX both let you kick off a date table from scratch. First, let's create a table by going to the Data view and opening the Table tab of the ribbon and selecting New Table. Let's start with Calendar Auto. I'll type in equals Calendar Auto and open the parens, and I can see from this tooltip that the only argument required is to define the fiscal year end date. So I'll type in 12 for December. Press Enter, and Just like that, this DAX function identified the oldest and the newest dates in our model and populated a calendar between them. Now, usually this works well, but every once in a while you'll end up with a calendar starting in 1901. So it's good to know how to define the outside dates when you need to. This time we'll use calendar. I'll type in equals calendar and I'll open my parens. And this function requires the start date and the end date, but it's looking for the date serial numbers, and I have no idea what that is. So I'll use the date DAX to figure out the serial number for me, which works just like the date function in Excel. I'll type in year and month and day of the start date, and let's do the end date in the same way. And press enter. Great! Now I have a custom calendar. Once the table has been started, we can now add the categorical labels that our users will want, like year and month. I'll just add a couple that should look familiar, like year. Equals year, open parens, and then I'll just indicate where this year DAX should get its date from. And we have years now. Let's do months, which works the same way. And hit enter. And I have my months. And while this was fairly easy using DAX, it's also possible to do this with Power Query, which comes with its benefits. One of the best reasons for choosing to do this in Power Query is that it is easier to populate all of the label columns. And Power Query writes the code for you in its language, which is simply named M. And after you've developed a calendar in Power Query, you can actually replicate the calendar anywhere else by simply copying and then pasting the M language. Let's head over to Power Query by clicking on Transform Data on the Home ribbon tab. And we can launch a new blank query using new source, blank query. This looks pretty blank, of course. And we will use the formula bar to enter our M formula. We'll start with a couple of M functions here. Equals list.dates, which will create a list of dates, of course. M is actually case sensitive, so I'm being super vigilant here. And then I'll open up our function parentheses to enter the dates. This also is going to be looking for a serial number, which I don't know off the top of my head, so we're going to use a function in M called date, which looks like this. Hash date with a lowercase d, open my parens, and then just like the Excel function, I need to type in the year, the month, the day. We'll close that up and enter a comma to move to the next argument. The second argument of the list dates function is the number of entries we want in this list. So the number of days we want in our calendar. I want this list to have 10 years worth of dates. So I'll just type 365 times 10, and I'll follow that with a comma. The last argument is where we define the length of each entry, and we want this to be a list of days. And I have no idea how to serially enter a day. So I'm going to use the duration function, which is another of those functions that are not capitalized and they're preceded by a hash. Hash duration, open the parens, and I'll type 1 day, 0 hours, 0 minutes, and 0 seconds. And close that parens and execute. Looks good. We'll make it official by selecting Convert to Table from the Home ribbon tab. And I'll just say no delimiters, and I want hanging columns to show up as errors, but we won't have any of those. Now we just need to rename this column. And I'm going to be very sure to confirm the data type is date, which is super important. We can do this on the Home tab in the Transform group, data type date. Okay, now we can easily add metadata from the Add Column tab, date. Let's add year and month and month name, quarter of year, day, and name of day. After you get started in Power Query, creating these labels is so much easier. Okay, looks good. Let's close and load it to the model. Great, we have our date table. Now we just need to relate it to our model. And before we forget, let's make sure to mark this table as the official date table by right-clicking on the table and choosing Mark as Date Table. When we do this, Power BI fortifies this table against common issues and confirms it meets the requirements to function properly as the date table. Earlier, we made sure to set the data type as date in our date table, and this is essential in order to allow your date table to talk smoothly with the other dates in your model. In fact, it's crucial that all of your fields are properly formatted for their data type, and that their settings are ideal for their purpose. For instance, let's say our customers are mostly based in Europe. Let's change the dates to display properly for Europe. In the model view, open up a table and select a field. The Properties menu is grouped into 3 different sections. Under General, the description becomes a tooltip when report builders hover over this field in Report View. We can also add synonyms for the Q&A feature, add this field to a folder to group relevant fields, and we can choose to hide it or unhide it from Report View. Formatting is where we change the data type, like to European dates. Or we could also change percent fields to always display as percent, or set up currency fields so that they always display as currency. Let's actually use these in Report View. Cool, the dates look good, and that percent is formatting nicely, and my currency. Cool, those work perfectly. But this other visual looks kind of funky. These are months, so I should probably display the month names here instead, I guess. Our report consumers might not know that these are month names. I'll just remove the month number here and replace it with month name. That's weird. It looks like this visual is ordering months alphabetically rather than by month order. That looks weird. Let's fix this. Back in the model view, under the Advanced tab, you can sort this column by another column. Great. We want this month name column to use the sort order from the month number column. Okay, looks good. Let's go see that in our report. That is much better. Other options in the Advanced menu include formatting locations as a specific location type, or formatting URLs and barcodes, and customizing how your numerical data will default aggregate. For instance, are your month day numbers summing? Set their default aggregation to none, and that'll fix that. Now when you add them to a report, Power BI won't calculate them. Also, discount percent. I never want to add that. I always want to average it. So let's set this default aggregation to average, and now its default behavior is actually useful. To wrap up this topic, let's scan and look at all the icons that are adorning each of these fields in Report View. By now, we should be able to visually confirm that each field is equipped with default behavior fitting its role. There's only one icon here that we haven't expressly covered yet, which is this one. This is a hierarchy, and often they are great, but some of them aren't great, and we need to know how to handle those. So we notice this hierarchy. See the year, containing months, containing days. But this wasn't created by us. This was created automatically by Power BI because it detected a data type that almost always gets segmented into successive levels of granularity, dates. Dates are almost always grouped by day, month, quarter, and year. So Power BI has been programmed to do that automatically. But some of these default behaviors can conflict with real-world practices. First of all, if our fiscal calendar doesn't start on January 1st, we should just totally disable this automatic behavior because none of those date hierarchies will be helpful to us. This can be done in File, Options and Settings, Options, Current File Group, Data Load, Time Intelligence section, and clear the Auto Date Time option. I'll just select OK. And in the Fields pane, let's notice that the date hierarchies are no longer available. Now that we know how to turn off a programmed column hierarchy, let's talk about how to manage organic hierarchies that appear within the data. We have one table for all company employees. Each employee's manager is shown here as well. But each manager is also an employee. So this is going to get a little weird. Let's look at Aaron. Aaron and his whole team, they report to their manager, Abram. That creates a many-to-one or children-to-parent data relationship inside this table. But Abram is himself also an employee, so he also shows up in the employee column. And he and his fellow store managers report to a regional manager named Abby, another children-to-parent relationship. And Abby and her fellow regionals report to a director, and so on. Because all levels of this hierarchy are tucked inside a single column, we won't be able to create an effective hierarchy unless we know how to flatten out parent-child hierarchies. The process of flattening out a parent-child hierarchy involves adding columns and using some awesome DAX that can identify and display the path from CEO all the way down to store employee. There are 2 DAX functions needed for this purpose, and while we will demonstrate them at the moment, you shouldn't feel pressured to understand them completely at this time. The important takeaway is that it's possible to flatten these out. Let's start by inserting a new column on the Modeling tab, and we'll input full path as the column name equals path, open parens, and we're going to tell it where to find the children in this path first. So that's on this same employee manager table in the full name column. Type in a comma, and then it's going to want to know where the parents are. That's on the same table in the manager column. Close out that parens and execute. Great. The resulting column shows the full pathway from CEO down to employee. Now we just need to extract each level into its own column using the path item data analysis expression. Let's create a column for each one and then enter the path item function. So the first one, let's make it CEO, and that function is going to be path item, open parens, name of the table, and then that full path column that we just created. And we wanted to take that very first level, close that, execute. Cool. All right, let's do regional managers next. Equals path item, open parens, the name of our table, and then this time we want it to take level 2. Close parens, execute. Awesome. Let's keep going. Now that we have flattened out this 1D column into a proper dimensional column structure, we will be able to run useful analytics and even design the proper Power BI hierarchies to allow users to drill down into this type of data. At this point, we have equipped some critical design skills in our tool belt. We know to keep things simple, both functionally and visually, and we know what to keep an eye out for and where and when to take action. Thanks for coming along with me on this design course. Can't wait to see what you do with your new skills.